So, a trend that we should know about intermolecular forces and the strength of IMFs is that the stronger the IMFs, then the more energy it's going to take to separate them. So, I want you to think about how the more infinity stones Thanos collected, the stronger he was getting, right? And the harder he was to defeat. So, it's the same thing here. And it translates into boiling point. So, boiling point is a temperature, and at that certain temperature, you will see a change from a liquid to a gas. So, the more intermolecular forces, think of a few slides back where we had more intermolecular forces and higher temperature. Think about that relationship and how it relates to this. So, the higher the BP, the boiling point, the stronger the IMFs. So the more IMFs you have to overcome, so the more kinetic energy you have to put in to overcome those IMFs. So now we're gonna start talking about the different types of IMFs. Now, there's a little bit of like technicality to how sometimes you will hear IMFs referred to, and they can also interchangeably be referred to as van der Waals forces, and this is referring to all these different types of IMFs. So if you ever hear that, just know it's just IMFs, intermolecular attractions, all the same thing. Now, in order of increasing strength, we have three different types of IMFs. We have dispersion forces, dipole-dipole attractions, and hydrogen bonds. We're going to talk about each of these individually. So let's say we could look at an atom with our naked eyes. We would find that atoms are not static. They're not just, the electrons are in one place, they stay there, they don't move. They're actually in constant motion. And this has to do, again, with something from Chem 1, quantum mechanics. And all this is that electrons can be in different places. So they're actually moving around all the time. And let's say we took some pictures of an atom, and obviously it's in motion, so they're going to be different, like frames, right? So here we have 3 frames. In the first frame, the atoms are kind of, one's closer to the nucleus, one's kind of on the outside, whatever, random places. And then in the second frame, they're kind of like on opposite ends, right? And then in the third frame, we see that they're kind of closer to each other. And because they're closer to each other, this actually causes a separation of charge. So you see how on this side we have a partially negative charge, and on this other side we have a partially positive charge. So what does this do for our intermolecular forces? So this actually causes a temporary dipole. So just to refresh on dipole, if maybe it's just sounding like a weird word to you, think of like the North and South Pole, 2 poles. So two poles, they're like completely opposite of each other. That's what happens here. Whatever molecules you have, any molecule, any atom, you will have temporary dipoles that can occur. And again, these are just unequal distributions of electrons that cause partial charges. Now, because of these temporary dipoles and the fact that it's happening to every single molecule or atom or whatever it is, then it can cause induced dipoles to other ones. So let's say you have one just floating around with a partially negative and a partially positive for a certain amount of time. It bumps into another one and it kind of induces a pole in the other one. So it's weird, but it's temporary, and they're not like permanent dipoles. But overall, what this causes is London dispersion forces. When this happens, these are overall London dispersion forces between molecules. So there's several different factors that can affect these dipoles that form and are induced in any molecule. And the first one is polarizability of electrons. Polarizability is the ability to kind of come to one side and form that partially negative charge. So think of that previous slide where we had the different frames of atoms, and that third frame you had 2 electrons that are kind of closer to each other. So they polarize to one side, right? and that caused a partially negative charge. So basically, the larger mass, and as I'm talking about this relationship here, I want you to look at this table. And on this table, we have increasing size noble gases. So we're starting at helium all the way to xenon. Xenon is obviously the biggest. And look at how the molar mass obviously is increasing along with it, but also look at the boiling point, how it's increasing, right? So the larger the molar mass, the more electrons you're going to have, obviously. The larger the electron cloud you're going to have. This is going to cause this atom, molecule, whatever, to have increased polarizability. So you can have a larger partial charge on it. This is going to cause stronger attractions. And again, stronger attractions means stronger IMF. So that means you can have you will have a higher boiling point because of that. And again, look at this table. You have the highest boiling point being xenon. So it makes sense that the biggest noble gas has the highest boiling point because it has the highest polarizability of it. So the second factor that affects induced dipoles is the shape of the molecule. So whether it is more branched and kind of like a circle type of overall shape, or whether it's a long chain. So the more branched it is, so this first one, for example, neopentane, then the smaller the area you're going to have between possible interactions between it and other molecules of the same type. Now, versus a very long chain version of a molecule, you will have more possibilities for them to interact, for them to like kind of bump into each other and form those induced dipoles. So the more surface to surface contact, then the larger the induced dipole, the stronger the attraction. So then the stronger the boiling point, or sorry, the higher the boiling point. So here we have actually three isomers. These are they have all the same chemical formula, but the difference between them is that they are structurally different, so they're bonded to each other differently. So you can see here that the boiling points are really different, and it has to do again with the shape of the molecule. So now we're going to do an example about how London forces affect boiling points, for example. So in this exercise, we are ordering the following compounds of this group 14 element and hydrogen compounds from lowest to highest boiling point. And then we have to explain ourselves. Now, I actually included this graph, which already tells you the boiling points. So all we're going to do is explain why, which is really important. This chapter, there is not any calculations, honestly. It's all about you understanding the concepts and being able to explain why. So here we can see that carbon has the lowest boiling point versus this, this carbon compound with hydrogens versus this tin compound has the highest boiling point, right? So why is this the case? Now, if we look at the order of these, carbon is actually the first in this group, and then it's silicon, and then it's germanium, and then it's tin. By group, I mean the order that they are in the group in the periodic table. So carbon is the first, so it's the smallest, right? And then tin is the biggest. So this has to do with molar mass, right? So the reason that the tin compound has the highest boiling point, and it's also the biggest, is because the bigger something is, then the more polarizable it is. The more polarizable it is, then the more induced dipoles that it can cause, and then you will end up having more London dispersion forces. So bigger molar mass means more polarizable, and this will cause more IMF, which causes a higher boiling point. So it's like a cascade of like reasoning, honestly. So you just got to get used to doing these problems to understand the connections between all of these things. So at this point, we finished talking about London dispersion forces and the factors that affect London dispersion forces. If you want to take a break right now, I would suggest pausing the video. I try to keep my videos as short as possible, but it's really hard. And I mean, when you think of like regular classes, in-person classes on a schedule, you have 3 hours of lecture every week. So me making one chapter into like 3 different videos that are total like an hour and a half versus when I get like 3 hours for one chapter in a week in regular classes, it's hard. So that's why I'm saying take a break. I know it's like hard to watch a video and keep the attention. So pause it, come back to it. That's fine. But if you want to keep going, the second intermolecular force that we're going to talk about is dipole-dipole attractions. And these occur between polar molecules. So you have to have polar molecules for this. London dispersion forces occur in any type of molecule, whether it's polar or not polar. But for this one, we have polar molecules. So overall, the criteria again are that you have polar bonds within the molecule and it's going to be asymmetrical. So you end up having a overall dipole moment on the molecule. For example, here on these molecules, you can see that that oxygen, it's actually the red circle that you see here. It causes an overall partial negative charge towards it. So what you end up having whenever you have many of these molecules is that you have kind of, think of it like a north and a south pole. So let's say the north pole is the negative pole and the south pole is the positive one. And because you have more of these and they all have these same north and south poles, then the north pole is going to be attracted to the south pole on the other one. So they all are like little magnets. That's how I like to think of it. Like, you know how magnets can have like a positive and a negative charge and they attract to each other, and versus, positive and positive repel each other. And that's what they are. So you end up having attractions between the positive end of a polar molecule attracted to the negative end of the neighbor. So how do dipole-dipole attractions affect boiling point and melting point? And this is just a theme in this chapter. The more intermolecular forces you have, the higher the boiling point or melting point. And here you can see that formaldehyde, which is polar, it has an overall dipole moment, has a much higher boiling point than ethane, which does not have, which is not a polar molecule overall. Now, ethane does have London dispersion forces occurring between molecules, but it doesn't have dipole-dipole. So formaldehyde has 2 different IMFs. It has the dipole-dipole attractions and the LDF, the London dispersion. Ethane only has London dispersion, so you can see this big difference in boiling point, and it's caused because of the fact that formaldehyde has an overall dipole moment, so it ends up having dipole-dipole attractions between it. So how do the dipole moments and how do the value of the dipole moments affect boiling point and melting point? So dipole moments can actually be like quantified, and it's like an arbitrary value, but let's say on an exam I were to give you a list of molecules along with their dipole moments, and I asked you to like rank the highest melting point or something. So here we have 5 different molecules, and you can see here that their dipole moment is increasing. How does it affect the boiling point? So as you can see here, acetonitrile has the highest dipole moment of 3.92, and it actually has the highest boiling point of around, what is it, 350, compared to propane, which has only a dipole moment of 0.08, and this is because it's actually nonpolar, so that's why it's so small. It's basically nothing. It has a boiling point of around 200. Notice that these all have a very similar molar mass, so it's a dipole moment that's affecting the boiling point in this case. So this next example is about dipole-dipole forces and the effects on boiling points. So again, just like the LDF example. Now in this one, we are predicting which will have the higher boiling point between N2 and CO. We're going to explain why. So
your very first job, honestly, for this is to probably draw out the Lewis structure. Now, I'm not going to break it down step by step, but you would first calculate your total valence electrons. So for N2, we would have a total of 14 valence electrons. If you do want to watch how to do this, please visit my YouTube channel or ask me, and I'll just send you the link on how to draw Lewis structures and how I'm doing this. But the total valence electrons for this one would be 14, and then you would go through the process of drawing it. I'm drawing it from memory. I'm not doing it actually step by step. And then for carbon monoxide, we would have, let's say, 4 and 6. That's 10 valence electrons that we would use up. And then we would have a triple bond and a lone pair and a lone pair. So these are the two structures. Now, we have to look at these and determine what types of bonds we have here. Whenever you have a bond between two elements that are exactly the same, that is a pure nonpolar covalent bond. So we know that that N2 bond is nonpolar. Here we have a carbon-oxygen bond. Oxygen is very electronegative, so this is actually a polar covalent. So this is pure nonpolar covalent. And then this one is just polar covalent. Now, because of this, this tells us that CO will have dipole-dipole, so I'm just summarizing DD, versus N2 will only have LDF. So because of this, because carbon monoxide has the dipole-dipole forces, which are stronger than LDF, and in addition to dipole-dipole, they also have LDF because every molecule has LDF, regardless if it's polar or not. This tells us that CO will have the higher boiling point because it has those dipole-dipole forces.
So before we talk about the final type of IMF, I do want to talk about this property called solubility. So we brushed on this topic whenever we learned about solutions in Chem 1. So we learned about what a solute is, what a solvent is. But solubility is what determines whether that solute actually dissolves in the solvent, right? And it all has to do with the compound and whether it's polar or nonpolar. So the main idea is that like dissolves like. By like, we mean polar and polar, nonpolar and nonpolar. Whenever you have two liquids that are alike, they're going to be miscible, so they're going to dissolve in each other. Whenever you have two liquids that are not, that are immiscible, so for example, something nonpolar and something polar, they're not going to dissolve in each other. And that's actually what you see whenever you add oil to water. You'll see that the oil just floats on top of the water. Now, the floating has to do with the density. Oil is less dense. And the fact that it doesn't mix has to do with solubility. And that is because oil is usually composed of hydrocarbons. So you can see here, for example, on this picture, we have C5H12. So that's pentane. And hydrocarbons are usually what oils are made out of. So this is an example of one, right, of an oil. And it's just floating on top of the water because it's not mixing. So compounds like water are actually polar compounds that have hydrophilic groups. So, for example, water has an OH group, but polar substances can have any of these groups, and they will only dissolve in other polar solvents that have similar groups, versus nonpolar molecules will only dissolve in nonpolar solvents. And hydrophobic groups, meaning nonpolar type molecules, they'll typically be CH, CC type compounds. Sometimes molecules can have both parts, and that will affect the solubility. Like it will be soluble in something polar to a certain degree, but not completely. But this is actually why oil and water don't mix. So if you've ever wondered that, now you know. So if you've ever placed a bottle of alcohol in the freezer, like a regular fridge freezer, um, you have probably noticed that it will cool down, but it will freeze. So why doesn't it freeze while water does freeze at the temperature that the fridge is at, the freezer is at? And this is because alcohol only has one point where it can hydrogen bond. So hydrogen bond is another type of IMF, intermolecular force. So water has two separate bonds in the molecule, right? OH and an OH, two of those, versus ethanol only has one OH bond within it. So because water has 2 points of like contact where it can form hydrogen bonds, like shown here, that means that it has more IMF. So it has a lower freezing point. So it takes less decrease in temperature in order to freeze it. Like it's already has a lot of attractions between it. So whenever you cool it down, it's going to be like, oh, okay, that's fine. I'll turn into a solid. I already have a lot of attractions right here between my molecules. Versus ethanol, it has less attraction. So it's like, you got to bring the temperature way, way down to freeze, to turn it into a solid. So, how can we recognize what molecules have hydrogen bonding occurring between as IMFs and which ones don't? So, we talked about water and how it has OH bonds. So, that is one of the types of bonds that can hydrogen bond. Another type of bond that you will see within a molecule that can hydrogen bond to another molecule are both the NH bonds and the FH bonds. So if you have molecules that have at least one of these types of bonds, they can hydrogen bond to each other. So the reason this happens is because not both, all oxygen, nitrogen, and fluorine, they all are very electronegative. So they hog all the electrons towards them, and this causes a really big like difference in the partial charges. So you'll have a really, really negative versus a really, positive, the poor little hydrogen with no electrons towards it. And because of this, it's like you have a really strong magnet compared to other polar bonds. These are like very strong. So what you end up having, because you have that really big difference, is similar to for dipole-dipole attractions, where you have like a little magnet. One end is attracted to the positive end of the other magnet. So what you can see here is that same type of pattern, but this one is just stronger compared to dipole-dipole. So hydrogen bonding is like a dipole-dipole attraction, but like in overdrive. It's just stronger, and it has these specific types of bonds, OH, NH, and FH. So I stated that hydrogen bonding increases boiling point and melting point. So now I just want to show you an example. So here we have ethanol and dimethyl ether. If you look at the formula for these two molecules, they have the exact same formula. So what's different between them? The way that they're bonded. They are called isomers, structural isomers. So you can see the structure up here and how ethanol has an OH group, but dimethyl ether is bonded in such a way where the oxygen is like in between the two carbons, so they're different, right? And because ethanol has this OH group, meaning it can hydrogen bond between each other, the molecules, this is going to increase the boiling point and the melting point. So look at the difference between the dimethyl ether and the ethanol boiling point. It goes from -22 for dimethyl ether all the way to 78. So it increases almost, like 100 degrees? Am I reading that right? And then the melting point goes up, not as much, but still, the melting point and boiling point are higher whenever you have a possibility of hydrogen bonding. So on this slide, I'm showing you the boiling points for group 15, 16, and 17 compounds, or group 5, 6, and 7, whichever way that you look at the numbers. But as you can see, here, for example, the blue line, that is group 16. So as you increase the period, right? So we're going down this group, so that means we're getting larger. So sulfur is smaller than selenium, and then selenium is smaller than tellurium. So as we increase the size, the boiling point is increasing, right? So the boiling point is highest for the biggest mass after, for example, selenium. So this would be dihydrogen tellurium. But notice that for each of these, and you have the same case for the other two groups, but notice that for each of these, the very first element that's bonded to hydrogen, right, is the highest. And why is that? So look at H2O, HF, and NH3. This is because each of these can hydrogen bond. So the ability for it to hydrogen bond, even though these are all smaller than their counterparts, so the very other end of the spectrum, they're all smallest, but because they can hydrogen bond, this increases the boiling point by a lot.
So now we're going to look at the effect of hydrogen bonding on boiling points. So we have these three compounds, dimethyl ether, ethanol, and propane. Their boiling points, not necessarily in order, are -42, -24, and 78. Match each compound with its boiling point. So what we have to notice is the types of bonds that we have in these formulas. So these formulas are condensed formulas that kind of show you how things are bonded. So in dimethyl ether, we have carbon like this, and then we have obviously the hydrogens, but we have these bonds right here that are important. These right there are polar bonds. So in dimethyl ether, we have, I'm just gonna write dimethyl, we have dipole-dipole, and obviously LDF by default. In ethanol, we have that CH3, CH2, and then that OH. That OH is the important part. OH shows you that you can hydrogen bond. By default, you have basically dipole-dipole and also LDF. And then finally, we have propane, which is nothing but carbon and hydrogen. So I'm not even going to write that one. If it's nothing but carbon and hydrogen, then that means you are completely nonpolar and you will only have LDF. So now that we know that ethanol can hydrogen bond, dimethyl can dipole-dipole, and propane only has LDF, IMFs, then we can match these up. So ethanol is going to have the highest boiling point. So ethanol, and I'm just going to summarize, would have 78.4. And then dimethyl ether, so I'm just going to write dimeth, would have the next highest, which would be -24.8. And then my last one would be propane. And the boiling point would be -42.1 degrees C. So first you would have to determine the types of IMFs each of these have, and then from there you can assign the boiling points. So in ion dipole attractions, and this is our last one, but it is important because it has to do with ionic compounds dissolving into, for example, water. So we learned about dissociation in Chem 1, and that is whenever you have an ionic compound and you put it into water. What happens to it? What actually happens to ionic compounds when they go into water, so for example, NaCl, it will dissociate into its ions. And the way that it arranges with the water is how this picture is showing you. So you'll have the negatively charged sides of the waters like arranging around the positive sodium cation, versus for the chloride ion, you have the positive sides of water arranging around it. And they both have around 6 waters arranging around it. So it's very like a very special type of arrangement and attraction. It depends on the charge of the cation or anion.